Hello ladies, gents, and everyones. It is Thursday, February 2nd, and we're here to talk about this week's space and astronomy news. It's only been a few years that we've been able to detect gravitational waves at all, with the first detection occurring in September 2015 at LIGO. But now we might be on the cusp of another gravitational wave breakthrough. So thanks to the very precise timing signals from pulsars, we can actually use them to detect very tiny fluctuations, such as the first ever detection of exoplanets. And so astronomers have been using those fluctuations to search for gravitational waves in our galaxy for almost 20 years, including as part of the International Pulsar Timing Array. Now, thanks to the long distances between pulsars, these signals would be sensitive to much lower frequencies than, say, LIGO or Virgo, helping probe the low-level background gravitational waves that permeate our galaxy from objects like distant supermassive black holes. However, this technique is really difficult, and so far it has not yielded any direct detections, but we have more information now about the noise. Now, you might be familiar with the concept of white noise. So white noise kind of occurs at all wavelengths, kind of like white light is at all wavelengths. But the background gravitational wave signal isn't expected to produce white noise. It's expected to produce something called red noise. So just like red light is at longer wavelengths, red noise is stronger at low frequencies. And the noise being detected by IPTA is red noise. So this doesn't necessarily mean that it's from gravitational wave signals. There are other things that can produce red noise. However, if they had detected white noise, that would have been a problem and would have been kind of back to the drawing board for some of our ideas about cosmology and supermassive black holes. So this red noise detection brings us one step closer to actually detecting gravitational waves using pulsars, which is really exciting. Some good news from Mars. We got confirmation late last week that those last few pesky pebbles had in fact been dislodged from the belly of Perseverance. And after several tests to ensure that the bit carousel is unobstructed, the sampling system is now up and running again. And the first thing they did with the operational system was get back on the horse and go back to that same rock and try the sample again. And it was successful on Monday. We talked recently about the first science targets for the James Webb Space Telescope, but the very first actual thing that the NIRCam instrument is going to look at is the star HD 84406. This is a G-type star about 250 light years away, located in the constellation Ursa Major. NIRCam will do this when it cools down to 120 kelvins. So there was actually a heater on the instrument to help keep optimal conditions during launch and travel, but now that it's at the L2 point, that heater just got turned off, and so the instrument is now cooling down. The NIRSpec and FGS NIRISS instruments were also turned on and their heaters turned off, while the MIR instrument has been on for a while. When NIRCam first looks at HD 84406, it is going to see 18 blurry points of light. And then that will slowly turn into one clear image of the star as the 18 primary mirror segments make minute adjustments to their position and curvature. It's a really exciting, although very slow process. If you haven't already, it would really mean a lot to me if you liked this video and subscribed to my channel. So this week marked the beginning of Black History Month, which we celebrate every February here in the US. And in honor of this month, NASA released an article highlighting African Americans in space. From Robert H. Lawrence, who likely would have been the first African American in space if not for his unfortunate death in an aircraft accident in 1967, to C.N.H. Proctor, who just made the trip to space last year as part of the Inspiration 4 mission. Something I learned from this article is that the first person of African heritage who went to space was Arnaldo Tamayo Mendez, a Cuban cosmonaut who went to space in 1980 as part of the Soviet Union's Intercosmos program. He was also the first Cuban, the first Caribbean, and the first Latin American to go into orbit, and he is currently a deputy in the Cuban National Assembly representing the Guantanamo province. So definitely check out the link below to learn more about these amazing astronauts. Trojan asteroids are small bodies that share the orbit of a planet at the L4 and L5 Lagrange points. Now these are most commonly associated with Jupiter because it has a lot of them, like over 1 million larger than a kilometer in size. But Earth actually has its own Trojan, a 300-meter asteroid that was discovered back in 2010. And now we know of another one. Actually, we've known of this other one for about a year now. It was first discovered back in December of 2020 and was proposed as a Trojan in January of 2021. But that has now been confirmed with a study that was published this week in Nature, which used archival data and new 2021 observations of the object to constrain its orbit and characteristics. They estimate that it will be stable as an Earth Trojan for at least another 4,000 years and that it's over 1 kilometer in size. So now Earth officially has 2 hangers-on. Actually, both of our Earth Trojans orbit at the L4 point, which is the leading point, so I guess Earth has 2 heralds now? You may know that Ax-1 will be the first all-private crew mission to visit the ISS, and it's scheduled to launch on March 30th. The crew has been in training since August of 2021, and now this week they've been approved as crew members by NASA and their identities officially announced. These are the 4 prime crew members, and they will spend 8 days on board the ISS conducting commercial, educational, and science activities, the details of which are still under review. As NASA's strategy for future low Earth orbit operations revolves heavily around a robust commercial space industry, this is a really important mission. NASA's Director of Commercial Spaceflight said this represents another significant milestone in our efforts to create a low Earth orbit economy. Good luck to the crew and looking forward to this launch. The cosmic microwave background is the sea of cold photons that surround us that are left over from the so-called surface of last scattering. That is the point at which the universe stopped being opaque, which was about 380,000 years after the Big Bang. We have made very detailed measurements of the temperature of the CMB, which is both remarkably uniform and very informative in its non-uniformities. Now, these measurements are of the local cosmic microwave background, but of course the CMB has existed throughout the history of the universe. Now, we can measure the temperature of the CMB back in time when we expect it to be hotter by looking at things that are farther away, although this is really difficult to do. We've managed to do it up to a redshift of about 3 or so by looking at how distant quasars are interacting with their local environment. Because light is redshifted as it travels through the expanding universe, we can use redshift as a proxy for distance and therefore look-back time. So now for the first time, we've actually measured the temperature of the CMB at a much higher redshift. A study published this week in Nature was able to measure the temperature of the CMB at a redshift of 6.34 by looking at the absorption lines of water in a distant galaxy. That's a look-back time of 12.8 billion years. They measured a temperature of about 16.4 to 30.2 Kelvin. For reference, the local CMB is about 2.725 Kelvin. Now, this temperature they measured is consistent with predictions from the Lambda CDM cosmological model. So this is a really cool measurement, pun sort of intended, and a new piece of data to help us understand this crazy universe that we live in. Well, that's all I have for you this week. Thank you so much for joining me, and I will see you again next week. Bye!